Atul, maybe you just in case, if you can record it.
Yes, yes, yes.
Do you have permissions?
Good evening, everyone.
With the HPE GreenLake, we have access to.
It's my great pleasure to introduce the speaker for today's Special Functions and Number Theory seminar. It's Professor David Bradley from University of Maine. David Bradley did his PhD from UIUC under the direction of Professor Harold Diamond, who is also present in the audience today. I think my first encounter with Professor Bradley's work is his early papers on Ramanujan's formula for odd zeta values. So on which I have also recently developed a lot of interest, and I have worked on some papers, and there his work was very useful for me. Today, he'll be talking on fractal subsets of Pascal's pyramids. Over to you, David.
Thank you, Atul. It's an honor and a pleasure to speak with you all and meet some of you. So I'm hoping the technology will work. It's been about a year since I've had to use Zoom during the pandemic, but planning to share the screen in a moment and present the slides. So I think it's just this green button down here, and we'll get started.
So, Gaurav, can you make him a co-host? Yeah, okay, yeah. Yes.
And I'm going to try to use the full screen for these slides, even though you can probably read them at 3/4 size. So I think that's going to be about as big as they get. Now I need to scroll back to the beginning. So let's see if we could go back to page 1. That's better. Okay. So yeah, this is a project one of many projects I've been working on off and on for a few years now. Many people have looked at the binomial coefficients modulo a prime typically, or a square-free modulus is sometimes considered. Things get a little more complicated with general positive integer moduli, but so I'm going to focus on just prime moduli, and then extensions, not just to the binomial coefficients in Pascal's triangle, but to multinomial coefficients and pyramid in quotes, because I'm not sure if there's a term in use for the corresponding geometry in the case of multinomial coefficients. So just to start things off, we'll look at the case of binomial coefficients modulo 2. This is not new, of course. Andrew Granville wrote a paper in the Monthly on Pascal's triangle and binomial coefficients modulo prime years ago, and so this is more or less just going to lead in and be discussing an extension of it. The counting formulas that I've come up with for counting multinomial coefficients in various residue classes modulo prime up to a certain number of layers in the pyramid, so to speak. The counting formulas I've come up with are an interesting application of elementary number theory involving the characters on the group of units in the field of primes modulo p. So in other words, the non-zero residues modulo p, you want to look at the characters, the character group. And then what you can do is relate the pyramid of residues modulo a prime to a corresponding subset of the unit cube, and take what's called the fractal dimension, and that's just an interesting side formula. So in Here's Pascal's triangle. I'm counting rows and columns starting with 0 instead of 1 as typical. It just turns out to be a little more convenient. And then what I'm going to do is reduce each of the entries modulo 2, so 0 if even, 1 if odd, and look at that infinite lower triangular matrix. We're just going to ignore the block of zeros where j exceeds I. And so the idea then is to look at the sub matrices consisting of the first 2 to the power k rows and columns for non-negative integers k. And when you focus on sort of these sub matrices with 2 to the power k rows and columns, you get an interesting pattern showing up. So to assist us in seeing this pattern, I've subdivided into blocks, block matrices. So you can see blocks of zeros in the upper right corner of these 4 sub matrices, and then in the sub matrices, another block of zeros in each of them. And in the non-zero blocks, you can also see there's some repetition going on. So basically, it's a recursion of sub-blocks that's taking place. If you define TK, say, to be the 2 to the k by 2 to the k block matrix, starting with T0 equals 1, then the TK plus first block matrix is formed by taking 3 copies of the TK block and then adding a block of zeros. This is not hard to prove. It basically arises from the Shue-Vandermonde convolution and elementary divisibility properties of the binomial coefficients modulo 2 in the case of the prime 2, but it extends easily to other primes. So this Shue-Vandermonde convolution formula basically tells you that you're getting in the next k plus first block, you're getting the recursion in terms of the kth. So then, having done that reduction modulo 2, we can basically shrink the whole triangle down into the unit square by subdividing it into 2 to the k by 2 to the k closed subsquares of side length 1 over 2 to the k, so scaling it so it'll fit in the unit square, and just evenly subdividing into these subsquares. This is the formula we want to use. It may look a little bit strange with the 1 minus I over 2 to the k and so forth, but that's simply because we typically look at the top row of Pascal's triangle and read down as you increase the rows, and in the XY plane you typically read up. So with those subsquares, then we want to simply define the closed set, call it FK, as the union of those subsquares, where the corresponding entry in Pascal's triangle is non-zero. So we have a 0 or a 1 mod 2 we're looking at, and we want to take the non-zero entries, and so pick up only the subsquares corresponding to the non-zero entries, and that union gives us that. And so here's an example, the first 32 rows and columns of Pascal's triangle mod 2. And here we've shown both the ones and the zeros in the lower triangular portion, but we're actually considering F5 or F32 to be the ones only. We're omitting the zero portions of the unit square. And you can see that it sort of looks like some pictures of fractals that you may recognize. Here's the next picture I've got with a few more rows. So 2 to the 10 rows, and now you can see the fractal nature of it starting to appear. So now we're just looking at the black squares or the black pixels. The white ones are not in the set. And so now what we want to do is take the limit, so to speak, and you can show that these subsets of the unit square, the FK sets, form a nested decreasing sequence. And each set in the sequence is non-empty, and it's a finite union of closed squares, so it's compact. And the intersection there is therefore a non-empty compact set, which we'll just call F. And we associate that intersection then with this limiting set with Pascal's triangle modulo 2, view it as a fractal, and then you can talk about its fractal dimension. So these are some quotes about fractals. I wasn't able to find a precise definition, but I think we all have sort of an idea of what a fractal is, and we've seen them, so maybe we won't linger too much on these pseudo definitions that I was able to locate in the literature. But so the definition I found in Barnsley's book is that it's the set of fractals can be associated with a complete metric space, say x comma d, where x is the set, d is the metric. And then what he does is he defines a collection of sets, script h of x, to be the set of non-empty compact subsets of the space. And so in the case of the unit square, for example, you can put a metric on it. You can put the Euclidean metric, or in our case, it's a little more convenient to use the square metric defined by the L infinity norm, where you just take the 2 points in the square and subtract the corresponding coordinates and take the max of the absolute values of the differences. So that gives it a topology, the metric topology on the unit square, and turns out to be complete. This is well-known stuff. And in that case, then the set of fractals, according to Barnsley, on this unit square would just be all the closed non-empty subsets of the unit square. So that's going to include things that we might not normally consider fractals, like the unit square itself. There's no holes in it, and we would normally not think of that as a fractal, but it's thrown in, I guess, just sort of to make the definition come out simply enough that it can be stated in this way. And of course, the unit square has dimension 2. So fractal dimension, then, how's that defined and calculated? So this may be maybe a little less familiar. What we can do is take this space of fractals derived from a complete metric space, take some set, non-empty compact set, and then for real positive real epsilon, we'll define this quantity curly n a epsilon to be the least number of closed balls of radius epsilon in the metric that are needed to cover the set. So in other words, by cover, we mean contained in the union of these closed balls. So take some set of points contained in the space, the metric space, capital X, and you want to cover the fractal A with a union of closed balls centered at points coming from the set. And so that means that the number of points we use to center these balls, or the number of balls that we use equivalently, should be at least this quantity Na epsilon, because the Na epsilon is the least number needed. And then for the fractal dimension, we define that in this rather strange looking way, perhaps, but you want to take the limit as epsilon goes to 0 through positive values. Natural logarithm of this Na epsilon quantity, least number of closed balls of radius epsilon needed to cover it, and then divide that by log of 1 over epsilon. And if that limit exists, then we call that the fractal dimension. So why this rather peculiar looking limit definition? There's some motivation for that. I think intuitively we might expect that a set with dimension capital D, say, would require roughly 1 over epsilon all to the dth balls of radius epsilon to cover it. If you think of the dimension being 2, for example, then if you shrink epsilon by a factor of 2, you expect that the number of balls needed is going to go up not by a factor of 2, but a factor of 4 if you're in dimension 2. Shrink the balls by 1/2 factor, then in dimension 2, you expect 4 times as many balls to be needed. And in general, 1 over epsilon to the D is what you might expect. So now if you just take natural logs on each side of that approximation, that gives you the relationship for the dimension D is going to be approximately this log of the number of balls needed divided by log of 1 over epsilon, and that motivates the formal definition of the fractal dimension.
Sorry, could I ask a quick question?
Sure.
Yeah, just the fact that, so I understand, yeah, I mean, it's, the analogy is very nice. As epsilon goes to 0 plus, do we expect this ratio to go up or go down? I mean, for fractals, it's obviously staying constant in some sense, but do we expect the ratio to go up or go down, and therefore the limit exists?
Wow, that's a great question. I guess I don't know. Yeah, I could almost foresee it depending on the set.
Right, yeah.
Yeah.
Wondering if that happens.
Yeah, no, I like that question, but I don't have a good sense of
Okay.
Yeah. No, I wouldn't consider myself an expert by any means in fractal geometry, but so just to disclaimer, when I got interested in counting the number theory side of it, Granville's paper inspired me to try to associate a fractal dimension with it as well. So I just kind of read up enough as I could to understand that part. But yeah, that's a great question. And I think in Barnsley's book, he extends it to the limb soup and so on if the limit doesn't exist. So
okay, there are subtleties. Okay.
Yeah, there are subtleties, definitely.
Okay, thank you.
And then they have these other techniques, because sometimes it's difficult to determine the minimum number of balls needed, even if you're in a square metric and your balls are squares. They have what's called this box counting theorem, where you can often get the fractal dimension by instead just covering the plane, or more generally Euclidean space, or whatever space you have, by non-overlapping squares or boxes. Just take a grid, and the grid size is a geometric sequence in the sort of the radius, and then you count the number of squares in the cover at a certain radius, where the interior of the squares in the cover should meet the set. And then if that limit exists, and generally the motivation for looking at these non-overlapping squares in a grid is that it's a little bit easier to count. And so then you just, instead of looking at the minimum number of balls, you're looking at the count for the number of squares whose interiors meet the set, and then taking the natural log as the radius goes to 0 geometrically. And if this limit exists, then it's going to have the same limit as the other. That's a theorem. So if we apply this this to the unit square, it turns out that you get the expected dimension for the unit square. It just turns out to be 2. The number of squares in a epsilon equals 1 over 2 to the k cover. If epsilon k is 1 over 2 to the k, then the number of squares whose interior meets the unit square is, not surprisingly, 4 to the k. And so when you take the natural log, the k comes out and the k's cancel, and you just get the expected dimension 2 for the unit square. No surprise. And then for Pascal's triangle mod 2, the sets we defined in their intersection, basically the fractal dimension there comes out to be, I'm not sure, can you see that formula? It's, or is the gallery inhibiting the picture there?
Visible? Yeah, it's visible.
It's okay.
Oh, good. Okay, so in my screen it's covering it, but I don't worry about that because I know what it is. So it's log 3 over log 2 in this case, and the reason that comes out is essentially due to the block matrix recursion. So the number of closed non-overlapping epsilon sub k equals 1 over 2 to the k by 1 over 2 to the k squares in the grid. The way the block matrix recursion is defined, you get the recursion starting with a0 equal 1, and then a k plus 1 is 3 to the k, because we have 3 copies of the sub matrix in the block matrix recursion. So that implies ak is 3 to the k, and then the k's come out of the logs and cancel. So we get log 3 over log 2.
Could I ask one more question? Sorry.
Sure. Yeah.
Yeah. Okay. So one comment as well. So the way I read about fractal dimension at some point was, if you double the size of the fractal, then how much does the area increase by? And you take the ratio of the logs. And this is exactly, as you said, Sierpinski's triangle.
Yeah, that's right.
If you double the side length, the area triples because the middle upside down facing triangle is removed, and you just get 3 copies.
That's right. Yeah.
So you get log 3 over log 2 from that side as well. And I probably think that there must be an equivalence between these 2 definitions.
Yeah, I think probably. I actually like your way of explaining it better than mine, but
simpler sounding.
Yeah.
But yeah, the other thing was about, so the question I had was about, if you go to the previous slide, or well, you don't need to, but sorry, the one before, the theorem about non-overlapping squares. Yeah. So so I assume there is a version for Rn as well, like R cube, R4. There could be fractals of higher dimension.
Yes, certainly. So this works equally well for R sub n, and then we'll just have n by n. Sorry, how do I say it? Yes, we'll have cubes essentially in n dimensions, the grid, and yeah.
And the same things. Okay. And is this related to the Hausdorff dimension, or am I just completely conflating 2 things?
Oh, the Hausdorff dimension. I'm trying to remember what that is again. They're not necessarily the same, is all I can remember about the Hausdorff dimension. Yeah.
Okay. Thank you.
So yeah, obviously you can do the same thing with a prime other than 2, and the fractal dimension in that case turns out to be related to the prime, it turns out to be log p plus 1 over 2 divided by the natural log of p for prime p. And the way that comes about is the block matrix recursion for a general prime p. It's a little more complicated, but basically the Schuh-Vandermonde convolution argument gives you this block matrix decomposition where the coefficients of the blocks are actually the coefficients, binomial coefficients in Pascal's triangle. And so at this point, we don't need to know what the coefficients are, just that when you count the number of squares in the cover, because of the number of blocks, number of non-zero blocks in the recursion, you're getting one. Whoops. What happened there? Back to meeting. I think I hit a button that I shouldn't have.
Maybe if you can press the left key or right key. I think the left key.
Which key?
Cursor, the cursor keys.
Cursor.
The cursor. Let's try this. All right, resume share. Sorry. Yeah, so the top row, obviously one block, the next row 2 blocks, and so on. So the recursion then is just the recursion just 1 plus 2 up to p times the previous number of squares to get the next number, and that's of course half p plus 1. So the explicit formula then for the number of intersections in the grid, so to speak, with the fractal set is going to be p plus 1 over 2 all to the k, just from that recursion. And then when you take the natural log, the k comes out, and you divide by the grid size. 1 over epsilon k is now p to the k, because your grid size is 1 over p to the k. And so that's where that comes from.
Sorry, just quickly, could you go back to the definition of this triangle? So we are just counting the squares which are non-zero. We're looking at the shape which is non-zero, mod p.
Yeah, that's right. Just the non-zero.
On the previous slide, I think this. No, sorry, one more.
All right.
And you just care about the fk.
Right.
The non-zero entries, right? The penalty, yeah, the second last line says that. And so so if you go back, then as p goes to infinity, this actually becomes 2-dimensional.
Yeah, it's
yeah. If you go back to the dimension of f, yeah, as p goes to infinity, I mean, I don't know what that means, number theoretically.
That's an interesting question as well, isn't it?
Goes to log p square. I mean, p square over 2. Log p square is twice log p. So
right. Yep. So actually, later on, I do want to look at what happens when p goes to infinity, but I wasn't. I hadn't thought of looking at the fractal dimension yet in that case.
And I'm wondering if the fractal dimension relates to some kind of number theory. I have no idea.
Maybe it says that most everything is included.
I think so, yes.
Right.
Because, yeah, obviously the unit square is mentioned too.
And does it make sense to look at this mod not primes as well, just divisibility or not? And if so, what do we get fractal patterns or something?
Yes, and yes, you do get fractal patterns for non-prime moduli. They in the square-free case, it turns out that the dimension is the dimension depends only on the largest prime factor in the square-free case. And so if p is the largest prime factor, of a square free modulus, then the dimension is going to have this same formula, log p plus 1 over 2 divided by log p. The other primes, the smaller primes in the square free prime factorization, just don't matter ultimately, which is kind of interesting. For the non-square free case, we, at least I'm not aware of any results, general results. So it's a little bit more mysterious what's going on. You certainly get sets that look fractal-like, but it's a little bit more complicated to try to determine what's going on with the counting is much more complicated in that case as well. So that's one reason why, I mean, for the square free case, yeah, I could have made slides stating that result, but basically it's what I said. You take the largest prime factor and it turns out to be that. There's a slightly more complicated counting argument you need, obviously, for that. But, otherwise, it's fairly straightforward. It's just for the non-square free moduli that we have a lot more work to do if we want to figure out what's going on. So I want to now scale up to multinomial coefficients, and just the setup there, n is going to be a positive integer. I think actually my n is going to have to be at least 2. Last night I convinced myself there might be a little hitch when n is equal to 1. In that case, instead of looking at dimension, Pascal's triangle sits inside a square, and if n is 1, then you're basically all your multinomial coefficients are 1s, and that's not very interesting. So that n is going to be the dimension, k is before non-negative, and p is a prime. And so now we want to look at an n-dimensional array with p to the kn entries, each n tuple of integers. We're going to have an n tuple of integers that'll just be denoting by alpha, and the components integers between 0 and strictly less than p to the k for each component. And then I'm just going to use c sub alpha for the corresponding multinomial coefficient. So the sum of the entries in the tuple divided by the product of their factorials, that's the multinomial coefficient. And so this is an example where n equals 2 again. So binomial coefficients. The main difference with the multinomial coefficients is, whereas with Pascal's triangle, I looked at I choose j. Here I want to look at I plus j choose I, or I plus j choose j equivalently. Just turns out to be a little bit easier to analyze with the multinomial coefficients if the sum of the denominator entries is used. And so basically what that does is it turns the Pascal triangle on its side, so to speak. So instead of displaying it vertically, we've tipped it on its side, and you're looking at diagonals of the matrix to get the Pascal triangle sitting inside. So little notation for the sets of multi-indices that I'm going to use. I'm going to index boldface n with a k if we're looking at positive integers from 0 up to p to the k minus 1. So I just want to keep in mind that we actually have p to the k integers in the sets n sub k. And so these sets n sub k to the power n, the Cartesian product is going to give us our set of multi-indices. And then if you chop off the Pascal pyramid, so to speak, after p to the k layers, and call that t sub k, that's just going to be the n-dimensional matrix of multinomial coefficients, where the multi-indices come from these sets. And then I denoted U by the non-zero residues mod P. And thinking of U as a set, we can choose the residue classes 1, 2, up to P minus 1, obviously. So then we want to define a counting function. So I just let n of T sub k comma U for a non-zero residue U to be the number of multinomial coefficients now in the first P to the K layers of Pascal's pyramid. The number of multinomial coefficients congruent to U mod P. And so that's our NTKU, and I've come up with a counting formula for this. So the theorem is that the number of entries congruent to U mod P in this sort of truncated Pascal pyramid is given by this interesting formula. You divide by the number of non-zero residues mod P, and then you sum over characters. So U hat is the group of complex valued multiplicative characters that basically map the non-zero residues into the non-zero complex numbers. So this is a familiar concept in number theory. And so then we have this factor lambda, which depends on the character and is raised to the kth power. And these lambda factors are given by this formula here. So you run over the non-zero residues, take the character, evaluate at those each of those non-zero residues in the sum. And then you have to multiply by the count. So this is counting when k is equal to 1, this is counting the number of multinomial coefficients in the first P layers. So when k equals 1, we're just looking at the first P layers where P is the prime. So basically, if you know what's happening in the first P layers of Pascal's pyramid, then you can, with this formula, deduce what's happening in the first P to the K layers for any non-negative integer K. And then we have this asymptotic formula for K going to infinity. It's basically you take the lambda value corresponding to the principal character, and that's this lambda here to the K over P minus 1. So lambda below with the principal character is just the sum over all non-zero residues, the number of multinomial coefficients in the first P layers, Pascal's pyramid. And it turns out that a simple counting argument, don't want to get into the details, but a simple counting argument gives you this formula in terms of the dimension n and the prime P. It's just a binomial coefficient. So example, in the prime 2, we have only one non-zero residue and only one character, the principal character. And so we get a nice formula, which in dimension 2 gives what we saw before, that there are 3 to the K odd binomial coefficients of this form in the first 2 to the K rows of Pascal's triangle. So another prime when P is 3, and the counting formula in this case gives you these values depending on the dimension n, and you work out the character counts and get these formulas involving the dimension n as well. And then that gives you these nice formulas for the number of multinomial coefficients in the first prime P is 3. So in the first 3 to the K rows, modulo 1, you get this formula, and then modulo 2, you get the pretty much the same formula, but with a minus. And of course, in dimension 2 with binomial coefficients, you can work out the numbers, the counts in the first, in this case, T1 refers to the first P rows. So P is 3 in the first 3 rows. That's easy to count. And then you get these formulas for basically twice the number of binomial coefficients in the first 3 to the K rows, mod 1 and mod 2. So it's kind of cool to have this character sum formula. I did one more prime here just to give you an example, because there's more characters and they're complex valued in this case. So when P is 5, there's 4 characters. And in dimension 2, again, you can easily count the number of residues in each of the classes in the first 5 rows, Pascal's triangle, and then you get these formulas for the number in the first 5 to the K rows in each of the residue classes. So in fact, these formulas were previously obtained by J. Roberts back in 1957, but he didn't have a character sum explicit formula for them. He did it by solving a system of 4 linear difference equations and 4 unknowns. So he had a different approach. So next, the idea is to subdivide the unit cube. Now, for the Pascal pyramid, the multinomial coefficients, we're looking at n dimensions, so it'll be the n-dimensional unit cube into non-overlapping subcubes. Look at the subcubes corresponding to entries, multinomial coefficients in the array congruent to whatever residue you're interested in. So U is one of the non-zero residues, then you want to look at only the subcubes corresponding to where the multinomial coefficient is congruent to that residue modulo the prime. Take the union of those, and then we want to intersect over all these. They, again, form a nested decreasing sequence. And in this case, the fractal dimension comes from the asymptotic formula for the count. So remember, the count is just getting you the number of, essentially the number of squares in the grid that covers the limiting set. And so when you take the natural log of this asymptotic formula, you get k log lambda. So there'll be a k factor in the limit definition for the dimension. So we get a k log lambda, and the prefactor 1 over p minus 1, that's negligible compared to the k log lambda term. And then in the denominator, when you calculate the frac 1 over the grid size, which is basically log p to the k or k log p. So the k log lambda and the k log p cancel, and we just get, in the limit, we get log lambda over log p, and that turns out to be this log base p of the binomial coefficient here, or you can write it in just by expanding the binomial coefficient as a product, sum of logs over log p. So that's kind of neat.
Sorry, so this is for every specific residue class, right? But in the previous case, you had looked at just non-zero, everything together. So if you take union,
yes.
The union is dimension, is there a formula for that?
So I think what you're asking is about whether the dimension depends on the residue class. Well, actually, it doesn't. So
it doesn't. No, I was asking if you take the union of all of these sets. That's the non-zero squares, right? In the 2-dimensional case. Yeah.
So if you take the union of these overall non-zero residues, it turns out that limiting set F, you get the same thing. So it doesn't depend on the limiting sets F don't depend on the residue, actually.
Oh, sorry. Yes, of course. The union is the same thing. That's right.
Yeah.
Okay, thanks. Yeah.
So just briefly, a conjecture relating to monotonicity properties of the fractal dimension formula that we obtain for the the Pascal pyramid. This DNP. You would think that by increasing the prime, you're going to get a greater proportion of the integers belonging to any one of the non-zero residue classes. That's obvious. So it would seem plausible that this is an increasing function of the prime, and in fact it is. But I did some graphing just to play around with this function. If we regard it as a function of the real variable p, you can plot it, and then I used x instead of p then, so we normally use x as a continuous variable. And so you can think of it as a function of x then, and it appears to have this sort of what's related to the concept of complete monotonicity, basically that it's non-negative and the derivatives alternate in sign. So that's in particular, it's going to be positive, strictly increasing, and concave down, but in general, it appears that these derivatives alternate in sign, and the technical word for function that satisfies these conditions is Bernstein. There's a whole book about Bernstein functions, and I started to read it and see if I could prove, based on what's known about these functions, they're related to completely monotone and absolutely monotone functions. But I wasn't able to prove that all the derivatives alternate in sign that way. The conjecture more generally is that if you take this ratio of log 1 plus ay over log 1 plus by, where a and b are in this range, that this is also going to be a Bernstein function. And if you can prove this, then you can prove the same thing about the fractal dimension formula that I got. So far, I haven't been able to do it. Got a partial result, but maybe want to skip on, because there's something else interesting I'd sort of like to show you before we finish up. So I just wanted to clarify how much time. I appreciate that you're willing to stay late for me, and it's
you can take 10 to 12 minutes. That's fine.
10 to 12 minutes. Okay. Yeah, that'll work. I just don't want to go over, because I know you have your lives to go to in the evening. And
no problem. Yeah.
All right. So just briefly, you may remember that we had these block matrix decompositions for Pascal's triangle, mod 2 and mod p, based on the Schuh-Vandermonde convolution. And it turns out there's extensions of the Schuh-Vandermonde and divisibility properties of multinomial coefficients that can be used to get a similar blocks matrix decomposition, where the coefficients in the decomposition, the C deltas that I wrote here, those are simply the multinomial coefficients. So this block matrix decomposition is key to how my counting formulas are developed. It leads to this kind of nice convolution where you're counting the number of multinomial coefficients in the k plus first block in terms of a convolution of the count in the kth block and the first block. So k layers, one layer, and that gives you the count in the k plus first layer. And so I prove it there, but I don't think we have time for that. I want to skip a few things. You know what characters are. So basically with my counting formula, I want to emphasize that throughout we've been counting multinomial coefficients modulo a prime congruent to a certain non-zero residue in, say, p to the k layers of Pascal's pyramid, but the count always relies on knowing how many are congruent to that residue in the first p layers. For a fixed prime, you can always figure this out either by calculating it, or sometimes you can find a counting argument that gives it to you. But it's kind of frustrating that I don't have a closed form formula that gives you this count in the first p layers for an arbitrary prime, an arbitrary non-zero residue, and an arbitrary dimension. It'd be nice to have a closed form formula. And I know that people have studied this question for binomial coefficients, and even in that case, it seems that if there is such a formula, it's going to be complicated. So here's some graphical evidence to convince you that if there is a formula that I've missed, it's not going to be simple. And so my first slide, and there's only one more after this, is show you a bar chart of number of entries congruent to a non-zero residue modulo a prime for each non-zero residue from 1 up to p minus 1 and various primes. So in chart A, we're taking the prime, what is it there? I can't read it. P equals 5 is going to be in the top. So there's 4 non-zero residues, and they're plotted. The bar chart, the height of the bars is essentially the number of counts of that residue in the first p rows of Pascal's triangle, so binomial coefficients. So you can see the residue 1 is occurring most frequently in all cases, and that makes sense because the first column of Pascal's triangle is all ones. So we looked at various primes, the selection there, p equal 5, 11, 41, etc., and plotted the bar charts. And so I'm going to try to blow this up a bit if I can, so you can see a little more. Whoop! How do I magnify this? Let's try zooming in. Maybe one more time. Yeah, so there's p equals 5. 1 is the most common non-zero residue, and then the other residues. And now we increase the size of the prime, so p equals 11. And now there are 10 non-zero residues in their counts. Again, the most frequently occurring residue is 1, as is expected. But then you look at the residue minus 1 in red, and it's starting to creep up as well. And as we increase the prime, you can see that it looks like the residue 1 is approaching 3p in frequency. The other non-zero residues in black, and then the residue p minus 1 or negative 1 approaching p in frequency, and then increasing the prime size even further. You can see the other non-zero residues other than 1 and p minus 1 seem to be settling down on p over 2 in frequency, but it's there's a fair bit of noise before this happens. So there's a lot of fluctuation about what appear to be the limiting values. And so I think what I'd like to do then is show you one more plot to illustrate this. It's a scatter plot. So now instead of looking at a few selected primes and all non-zero residues, in this case, we're looking at just a few selected residues and a whole bunch of primes, basically every odd prime up to 10,000. And now we're looking at just the residues 1, p minus 1 over 2, p minus 1 or negative 1, and p minus 2. And so the residue 1 illustrated here in the top left looks like the slope of the scatter plot for various primes is approaching 3, as we expected in the previous bar chart. The number of binomial coefficients was approaching 3p for the residue 1, so the slope should be 3. For the residue p minus 1 over 2, the scatter plot is clustered around a straight line roughly with slope 0.5, but you can see there's a lot of noise. Residue minus 1 or p minus 1 here, slope about 1 again, but lots of noise. And then for the residue p minus 2, that's sort of another sample of a residue other than 1 or minus 1. So again, scatter plot, but it looks like the same slope of 1/2. So the conjecture is that if you look at binomial coefficients, we're going to let NKPU be the number of binomial coefficients in the first p to the k rows of Pascal triangle, which are congruent to U, modulo the prime p. And then just focus on the first p rows, so N1. The conjecture is that as the prime p goes to infinity, we get this sort of split into 3 different cases. So basically, the conjecture is that the ratio goes to 3 for the case of the residue 1. It's 1 in the limit if the residue is minus 1 or p minus 1. And we believe it's 1/2 for all the other non-zero residues. But so far, this is just a conjecture. We don't really know how to prove it. It seems reasonable that the residue 1 is going to be much more frequent than the others, but why it should be exactly 6 times as frequent as all the others, apart from p minus 1, we don't know why it should be 6 times more frequent.
David, have you ever tried averaging over the U?
Averaging over the U. So, yeah, that's an interesting idea. So what would you expect? What would you expect would happen there? Let me think.
Well, from your data, I suggest the average would be 1/2.
Yeah. Yeah, that seems like something one should be able to prove, actually, by averaging over all the U's. Yeah, that's a good suggestion. Yeah, I don't know. It's interesting because the difference in relative frequency is sort of dissipates the more rows you take. So if you let k go to infinity, our asymptotic formula proves that they all occur ultimately with equal proportion 1 over p minus 1. So the fact that just in the first p rows we get these pronounced differences is kind of interesting, but the effect dissipates as you take more and more rows.
Have you tried N2 as well for N2? They have the same, there should be some limiting at each k.
Right, yeah, definitely. That's something we have not investigated, but it would be, I like that idea. It might actually tell us more about what to it might guide us to an idea what to look for if we looked at bar charts and scatter plots for the next. So N2 would be P squared rows essentially. Yeah.
I mean, N2, N3, N4, each of them hopefully has stable limits. But
Yeah.
at what point?
Yeah. Yeah. I mean, if I wanted to be greedy about it, I would say, why look at only powers of the prime number of rows? It would be nice to have a formula that would tell you how many in any number of rows, right? But that just seems completely out of reach.
Yeah, but your fractal structure, your self-similar structure, recursive structure probably means at least the prime powers are the right things to look at least as a start.
Yeah, exactly. Yeah, good point. Yeah. Yeah, so I basically I think I should stop here, but if any of you have further thoughts or ideas, please feel welcome to contact me. And I'm still working on this now and then when I get time off from teaching and during the break and summers and so forth.
So, David, I have a question. Have you tried this for Sterling numbers?
Oh,
They have very similar thing. And, I sent you a picture. At some point, I was making a program, just learning programming. And I tried the Sterling numbers and they look exactly the same. The triangles were kind of, bent or something.
yeah, that's interesting because the Sterling numbers, I think they have a somewhat similar two-term recurrence.
Yeah. They're almost the same, except there's some K or N attached to one of the terms.
Yeah. So
you get very similar stuff. I mean, the pictures, they come out very similar for the binomial, for the Pascal case.
yeah.
So certainly your techniques will work there. But I don't know, beyond that also perhaps would be fun. See.
Yeah.
I had one other question a few slides back. You talked about Pascal's pyramid, of course, for prime powers, for prime power layers. And the question is very simple. You looked at it for primes, but how about again for square free stuff? Did you see any higher dimensional? Does it not depend again, except the largest prime factor, the largest two prime factors, maybe?
So yeah, you're asking about with the multinomial coefficients.
That's right.
Yeah, look at square free moduli.
If you take square free, yeah.
Right. Yeah, I haven't looked at that. I'm sort of hopeful that a similar counting argument, basically I had to squeeze the counts, find upper bounds for the counts and lower bounds for the counts in the case of dimension 2 Pascal's triangle and binomial coefficients. For square free, any finite number of distinct prime factors, right. The largest prime is all that matters in the limit. But for multinomial coefficients, I haven't investigated. I'm hopeful that a similar, probably more complicated, but a similar type of bounding argument would work in that case as well. But it's an interesting question. So yeah, go ahead.
David, I had one question. Can you go to the slide where you mentioned about complete monotonicity?
Sure, let's go back to that. Okay, so
okay, yeah. So we have this DN Bernstein. So does it give any measure, interesting measure, like the Widder's theorem says about
representation of CM functions?
Yeah.
Oh yes. So you're referring to the fact that a completely monotone function has a representation as the Laplace transform of a non-negative measure?
Right. So,
Yeah, go ahead.
so I mean, it would be a good idea to see what the measure looks like.
Yeah. I remember trying to see if I could find the corresponding measure, and I didn't spend a lot of time on it because I'm not expert in that sort of stuff. But yeah, that would be interesting to see if there's a corresponding measure for this DN function, and presumably if you could find it, that would easily dispose of this this monotonicity conjecture. Yeah.
How does it
one slide?
Yeah.
Just the definition of DN again.
Yeah.
So the definition of the DN extended to a positive real variable X is just this. In terms of the button.
Yeah, this complete monotonicity, if it is established, it will give a new class of functions, because generally many people work on quotients of gamma functions or related stuff as far as proving complete monotonicity is concerned. But I guess this seems to be a completely different type. So it'll be...
I'm a little bit disappointed that something as simple as, which it boils down to, just this ratio of logarithms. I've been a little disappointed that I haven't been able to find anything directly applicable in the literature. There's a considerable number of papers, and there's even a book devoted to Bernstein functions with a huge number of a table of various functions which are known to be Bernstein or completely monotone and so forth. I couldn't find anything that seemed to be applicable to this, and you would think somebody would have thought of it or come up with it. But anyway, there's obviously the question itself of looking at Pascal's triangle modulo P seems kind of recreational, but just the mathematics involved in extending to multinomial coefficients, I was surprised that this beautiful character sum formula came out of it, and lots of interesting questions still seem to be unsettled with counts and so forth. So that's sort of what kept me interested in working with it and trying to prove new things. So it's been a pleasure sharing with you. Oh, it looks like there's a question in the chat. Most orthogonal polynomial systems satisfy a binomial type theorem. Q prime
of x plus y equals summation n choose r q minus r prime of x times something else of y.
Yes.
See, what I mean to say is, if you take an orthogonal polynomial system Qn, then Qn of x plus y is sum of NCR, QRx, Qn minus Ry. So
Q.
they satisfy binomial coefficient relation. Most orthogonal polynomial systems do that. And some of them do that interacting with other orthogonal polynomial systems also. QR, you take one, and then some another system, gamma n minus r in another at y. So such coefficients are very useful in orthogonal polynomial systems also. So do your results have applications there too?
Yeah.
And I have said that before in this group. So it is repetition for many people sitting there. Like you take Jacobi system, Jacobi system, Laguerre system, many other orthogonal polynomial systems, they all satisfy this binomial relation.
Right. Yeah, thank you.
Thank you for the interesting talk.
Thank you.
Any further questions? If not, let's thank David for a wonderful talk.
Thank you all. It's been a pleasure having you, and hey, look forward to possible future collaborations. Who knows?